Hello again, my name is William Pye, and in this video we're going to be talking about the properties of the connectives. Over the last couple videos we've introduced the logical connectives, and we've also introduced the symbols that represent the logical connectives, but we ended with a couple questions that I hope to address here. First, parentheses, when are they necessary and when can they be safely omitted? Is there a priority of order for the logical connectives and how they must be evaluated? And moreover, how do the logical connectives interact with one another? To do so, we're going to study the properties of the connectives and see if there is a way that we can intuit the answers to these questions. As stated, after introducing the symbols for the sentential connectives, how do those symbols interact with each other? That is, what statements using those symbols are always true? As such, we're going to introduce the following notions, what's called a tautology, a contradiction, and a contingency. Now, after those notions are discussed, we're going to actually show that several properties are going to hold for the negation, conjunction, and the disjunction. Now, you may notice that I did not say anything about the implication or biconditional. Now, the reason being is that we're going to hold implication and biconditional for another time to be discussed. Now, the reason for this, there's actually two. The first reason is time. I don't want this video getting too out of hand in terms of length, but the other reason is that the implication and biconditional play an integral role into actual logical deduction and building proofs. And as such, I want to set those aside and talk about them at a later date and give them a much more detailed analysis. To motivate tautology, let's start with a good example. Recall that a sentence can be either true or false. This declaration is actually known as the law of excluded middle, and in symbols, the law of excluded middle can be stated in the following way. That is, P disjunction negation P. That is, either P is true or P is not true. That is, P would be false. Now, let's look at the truth table for this particular expression. You have P, negation P, and then the disjunction of the two of them. If P is true, the negation of P will be false. And if you take true disjunction with false, you get true. On the other hand, if P is false, negation of P would be true, and false disjunction with true will give you true. Now notice, that final column, the actual expression of the law of excluded middle, is true regardless of what the proposition P happened to be, which motivates the following definition of something that's always true, what's called a tautology. A sentence is a tautology if and only if the result of replacing any of its component atomic sentences by other atomic sentences always yields a true sentence. That is, a tautology is a statement that regardless of what its component sentences are, is always true. On the other hand, no sentence can be both true and false simultaneously. This fact is the law of non-contradiction, and in symbols, the law of non-contradiction can be stated in the following way. That is, the negation of P conjunction negation P, like so. So notice the placement of the parentheses here. This is very similar to the law of excluded middle, except rather than having a disjunction, we have a conjunction, and there's an extra negation floating outside the entire expression like this. Now, let's take a look at the truth table for this. If P happens to be true, negation of P will be false, and the conjunction of true with false will give you false, and the negation of false will give you true. On the other hand, if P happens to be false, the negation of P would be true, the conjunction of false with true will give false, and the negation of false will give true. Notice that the final column is all true, meaning that the law of non-contradiction is also a tautology. Now notice that the statement P conjunction negation P is always false. That is, that penultimate column was all falses before they became all trues. Now that motivates a particular definition, what's called a contradiction. A sentence is a contradiction if and only if the result of replacing any of its component atomic sentences by other atomic sentences always yields a false sentence. It's basically the opposite of a tautology. A tautology is always true, a contradiction is always false. Now, what if you're neither? Well, then you're contingent or dependent on the situation. A sentence is contingent if it is neither tautology nor contradiction. It's true some of the time and false some of the time. So it's situation dependent. These are the ones that you have to pay much more close attention to because they're not always one or the other. Now, I do want to throw out a bit of a warning, and that is the two Suppes textbooks that I've been making reference to more narrowly define contradiction to be precisely a sentence of the form P conjunction negation P, as opposed to Magnus, who says a contradiction is any statement that is always false. So keep that in mind when bouncing between the different textbooks there. Now, our main attention will be on tautologies, though contradictions and contingencies will be addressed as we need. Before diving into the properties of the connectives, here are two more examples that will prove useful in the future. First, a true statement in a disjunction automatically guarantees a true sentence overall. Basically, the trueness of the one statement absorbs the other statements in a sense. So, for example, take a proposition P, and I want to disjunction that proposition with something I know is true, a purely true statement. If that happens, well, if P is true, true disjunction with true is true. On the other hand, if P happens to be false, false disjunction with true is also true, giving me a tautology. Notice that the trueness of P becomes irrelevant if I know that something else in the disjunction is true automatically. Consequently, one trueness absorbs all others in a disjunction. Likewise, false statement does the same thing for conjunction. So that is, if you have a false statement show up in a conjunction, it absorbs all of the other statements, making the entire conjunction false. So let's take a look at it. So if I have a proposition P, and I conjunction with something I know is false, well, if P is true, then true conjunction with false is false. On the other hand, if P is false, false conjunction with false is also false, giving me a contradiction. The falseness in a conjunction absorbs all of the others, making the entire statement false. So both of these are absorbing in a way. True absorbs everything else in a disjunction, false absorbs everything else in a conjunction. Turning attention to the properties of the connectives, let's consider swapping disjunction and conjunction in the previous examples. That is, disjunction with a false statement and conjunction with a true statement. What happens then? Well, notice that a disjunction of a given statement with a false statement agrees with the original given statement. That is, the false statement acts trivially. It basically contributes nothing new to the disjunction. Let's take a look at that. If I give you a proposition P, and I disjunction P with something that I know is false, well, if P is true, then true disjunction with false gives me true. On the other hand, if P happens to be false, false disjunction with false gives me false. Notice that these two columns are identical, so that means I should start looking at the equivalence. So when are they the same? Well, true and true are the same, so this is a true statement. True equivalent to true is true. Likewise, false equivalent to false is also a true statement, giving me a tautology. Notice that the false basically melts away and just leaves me with the P. The false contributes nothing, basically. And the same is true if you have a true statement under a conjunction. Let's look at that. If you have a proposition P, and you take P conjunction with something that's true, well, if P is true, true conjunction with true is true. On the other hand, if P is false, false conjunction with true also yields false. Thus, you look at these two, and I look now at the equivalence. True is equivalent to true, so that gives me a true statement. False is equivalent to false, gives me a true statement. Notice that this is also a tautology. That is, conjunction with the true statement basically melts away. It's not needed. These act what we might call as identities. False acts as an identity for disjunction. It melts away, leaving me with what I started with. And the same thing is with true. True acts as an identity for conjunction. The next property comes from a classical figure of speech, what's known as the litotes, or the double negative. So, a litotes is a figure of speech that utilizes two negative terms in order to understate some certain fact. Now, you've likely heard some litotes in your time. It's very common in parlance to actually use litotes. For example, the film is not bad. So, this is understating the fact that the film had some kind of good merit to it. The example does not disagree with the theory. So the example does not prove or is not monumental, but it is not against the theory. Lastly, you see this in song lyrics as well. It's not unusual to be loved by anyone. This is an understatement of the fact that there is some usuality to this. In logic, the litotes resolves to become precisely the original statement, not some kind of understatement of it. So let's actually take a look at the truth table for this. If I have a proposition P, and I look at negation P, well, what happens is if P is true, negation P will be false. If P is false, negation P will be true. What happens if you negate again? Well, the false becomes true, and the true becomes false. And notice that the first column and third column now have the same values precisely. So I look at the equivalence. True equivalent to true is a true statement. False equivalent to false is also a true statement. Thus, I end up with a tautology. Basically, if you negate a negation, you get back to the original precisely. That is, the negation as an operation is self-inverting. It undoes itself. While negation is self-inverting, every statement is idempotent under conjunction and disjunction. Now, where that comes from? It comes from the Latin idem and potens, meaning self or able, basically self-capable. Thus, if you have something that operates on itself, it becomes itself. That is, the repetitions contribute nothing new to conjunction and disjunction. You can remove repetitions with no cost. So let's take a look at that. Say I give you a proposition P, and I look at P conjunction with itself. Well, if P is true, true conjunction with true is true. False conjunction with false is also false. Notice that these columns are the same. So if you look at the equivalence, true equivalent to true is true, and false equivalent to false is also true, giving me a tautology. Now, if I do the same thing for disjunction, basically the same thing happens. If P is true, true disjunction with true is true. On the other hand, false disjunction with false is also false. Notice these are the same. So if I look at the equivalence, true equivalent to true is true, and false equivalent to false is also true, giving me another tautology. Basically, if you have repetitions of the same proposition, you can throw away the repetitions with no cost. Now, the conjunction is a binary connective. That is, it takes two statements and glues them together. But any number of statements can be joined by iterating the conjunction upon itself. For instance, I could start with P. I could then conjunction on the right by Q. I could then wrap that in parentheses and conjunction on the right by R. I could wrap that in parentheses and conjunction again, and basically make this chain of conjunctions in ever-expanding parentheses. However, this is not the only way you can do this. For instance, I could start on the other side, start with R, then conjunction on the left by Q, wrap that in parentheses and conjunction on the left by P. I could wrap that in parentheses and conjunction on the left again, basically making the same chain but extending to the left rather than to the right. I could be fancier, start in the middle, in which case I could conjunction on the left, the right, left, then the right, and then just alternate left and right like that, making yet another grouping. And the important question here is, do the groupings make a difference? The parentheses essentially imply a higher order of operations, that here the P and Q would happen first and the R second. Over here the Q and R would happen first and the P second. So does the order of those evaluations matter, or can I drop the parentheses completely? Thankfully, no. The grouping of the conjunctions does not matter. Now, demonstrating this property is tedious because there are three factors, each of which can be true and false, giving you 8 different cases. But if you remember the absorbing property from earlier, that actually makes a lot of these cases go by fairly quickly. So let's start at the top. If I have all trues, so true, true, and true, then I'm going to start by conjunctioning P and Q and then conjunction the result with R. So true conjunction with true is true, and then conjunction with another true gives true. However, the minute a false enters into this, while true conjunction with true will give you true for the first part, conjunctioning with that false will give you a false. Now keep going with that. True conjunction with false will give you false, and no matter what you conjunction with, that ends up giving you a false. And keep going. True and false gives false, which yields a false. False and true conjunctions to give you a false, which gives a false. False and true again gives you a false, which yields a false. Double false gives you a false, which gives you another false. And false gives you a false, which leads to a false. So notice, at the beginning you have, when everything is true, you get a true. But the minute any false creeps in, you have the rest of the table ends up being false. Now, what happens when you regroup things? What if I did Q conjunction with R, and then I take the result in conjunction with P on the left? Well, the same thing's basically going to happen. If you have true and true, that will give you true. And then conjunction with another true will give you true. But the minute a false sneaks in, true and false gives false, which leads to false. False and true will give false, which leads false. False and false gives false, which leads to a false. Now, what's going to happen here is true and true will make a true, but now P is false. Conjunction with that will yield a false, and that basically is the moral of the story from here on out. True and false gives false, which leads to false, which leads to false, which leads to false. As before, you have true on top, the rest is false. So this column and this column are identical. True on top, false from there forward. So if I look at the equivalence, true equivalent to true is a true statement. False equivalent to false is also a true statement, and that's the same for the rest of the table. Now, This property is what's known as the associative property. The reason being is because it comes from the same Latin root as the word social, that is, as in social grouping. So, being asocial, that is, associative, the grouping doesn't matter. The grouping here does not matter. This is what we call the associative property. Similarly, the disjunction is associative as well, meaning the grouping does not matter. Now, this is tedious to show also. You have 3 factors, each of which can be true and false, giving you 8 cases. But there is an absorption property happening here. The minute a true appears, the entire disjunction will absorb into that true. So, let's go ahead and work through some of this fairly quickly. Specifically, if you have P disjunction Q, I take the result and then disjunction with R. So if I have a true, well, the minute I disjunction a true, I will get a true, and then no matter what I disjunction that true with, will give me a true again. So, true to true gives me true, which gives me another true. So, true and true gives true, which gives me another true. True false gives a true, which gives me another true. True false gives a true, which gives me another true. False true gives me a true, which gives me another true. False true gives me a true, which gives me another true. Now, here's where it gets a little bit more sticky. If you have false disjunction false, that gives a false, but if you disjunction with a true, that gives you true again. The only one that's truly interesting is the last one. False disjunction with false gives me false, which disjunction with a false will give me false. Now, notice this column is all true, except for a single false at the bottom. So notice that this is almost the reverse of the chart that we had on the last slide, actually. That was a true and then a whole bunch of falses. That might come into play later. But for now, let's regroup this and see what happens then. I'm going to have Q disjunction with R, and then I'm going to take the result and disjunction on the left by P and see what happens there. So what's happening here, again, a single true is enough to make it true. So I have true disjunction with true, which gives me true, which will yield a true. True false gives me true, which gives another true. False true gives me a true, which gives me another true. Double false will give me false, but P is true, which triggers this to be true. From here, I have double true gives me true, which gives me true. True false gives true, which gives true. False true gives me true, which gives me another true. And then the only one that's interesting is the last one. So false and false give me false. Disjunction with a false gives me false. Notice it is true all the way down, except for the final false. If you compare this column with this column, they are identical. So if I look at the equivalence, I have true equivalent to true is a true statement all the way down the road, and then false equivalent to false is again a true statement. This is now a tautology, which shows that the disjunction is indeed associative, the same way the conjunction was. Please note that associativity kept the order of the statements the same. For instance, in this conjunction, you have PQR and PQR. The only difference is that here P and Q are grouped, here Q and R are grouped. Same with the associative law for the disjunction. It's PQR and PQR. Here P and Q are grouped, here Q and R are grouped. That does beg a question, though, and that is, if I was to swap the order of the statements themselves, rather than having P then Q, what if I swapped them and had then Q then P instead? If I was to physically change the order of the operands, would that make a difference? And no, not at all. If you change the order of the operands, it actually doesn't make a difference. So let's see that with the conjunction. So if I have P and Q, let's look at P conjunction Q. Remember, P conjunction Q is only true when both are true at the same time. So double true will give true, true false yields false, false true gives false, and double false yields false. Now, switch the order. If I was to put Q then P, what happens now? Well, remember, it is only true if both are true. So double true will give true, all the others will yield false. So false true gives false, true false gives false, and double false gives false. Notice these two columns are identical. So if I look at the equivalence, true equivalent to true is a true statement, false equivalent to false is a true statement, false equivalent to false is a true statement, and false equivalent to false is a true statement, giving me a tautology. So indeed, the order of the operands themselves does not matter. This is what we call the commutative property. Commutative because it shares the same root as commuter. They have commuted, they have physically changed locations from one place to the other place. Thus, we call this the commutative law. Also, the disjunction is commutative, so the order of statements does not matter, so let's take a look at that. If you have two statements, P and Q, and you look at the disjunction, remember the disjunction is only false when both are false simultaneously. Thus, if you have double true, that yields true. True false yields true. False true yields true. And double false is the only case that you yield false. On the other hand, switch the order. Remember, it is only false if both are false simultaneously. Thus, double true will give true. False true will give true. True false will give true. And double false is the only case that you get false. Notice that these two columns are identical. So if I look at the equivalence, true equivalent to true is a true statement all the way down until I get to false equivalent to false, which is also true, giving me the tautology. Hence, the disjunction is also commutative, just like the conjunction. So far, only a single connective has been considered at a time. For example, with associativity, you had conjunction on itself, or disjunction on itself. For litotes, you had negation on itself. But what happens when these different connectives interact with each other? For instance, what if I have a disjunction followed by a conjunction, or a conjunction followed by a disjunction, or a negation on top of a conjunction, or a negation on top of a disjunction? What happens in each of these? Well, turns out for all four cases, the outer connective is duplicated to each statement of the inner operation, effectively distributing amongst them. So let's take the first example here, which is P disjunction Q conjunction with R. Now this is going to be tedious because there are 3 factors to deal with, each which could be true or false, giving 8 distinct cases. But if you exploit some of the absorption laws from earlier, it turns out this calculation can go fairly quickly. So in particular, notice that if the disjunction or R is false, the conjunction immediately becomes false. So also, if you have either P or Q is true, the disjunction becomes true. So starting with true, 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 the disjunction will be true, and then the conjunction will be true since both of these end up being true. However, if R becomes false, the conjunction immediately becomes false, even though the disjunction was true. Here, the disjunction ends up being true, but conjunction with a true gives you true. However, conjunction with a false gives you false, even though the disjunction itself is true. Flipping that around, the disjunction will be true, conjunction with a true gives you true. However, conjunction with false will give you false. If you have double false, the disjunction is false, immediately making the conjunction false, and double false here will make the disjunction false, making the conjunction false as well. So here's what the result ends up being. True, false, true, false, true, false, false, false is the actual result of all possible combinations. Now, if one was able to distribute, here's what you would get on the other side. You'd have P conjunction with R, Q conjunction with R, and then disjunction the results. If R is false, both of these columns become false, making the disjunction false. If P or Q ends up being false, that'll falsify only its column. So, in the case of all true, then these two conjunctions will be true, giving a true disjunction. However, if R is false, both of the conjunctions become false, making the disjunction false. Here, what happens is Q ends up being false, which will falsify its column, but P happily ends up being true, and the disjunction becomes true. R, however, becomes false here, which makes both columns false, making the disjunction false. Next, P becomes false, which makes this column false, but Q is true, making this column true. So true disjunction false ends up giving me a true. However, R here becomes false, making both false, making the disjunction false. The last 2 rows, however, these falses will make both columns false, making the disjunction false. Notice I have the same pattern. True, false, true, false, true, false, false, false. Since these match, if I look at the equivalence, all of these rows will end up being true. True equivalent with true gives me true. False equivalent with false gives me true, all the way down the road, giving me a tautology. Thus, one can say that the conjunction distributes over the disjunction. Interestingly, the reverse is also true. That is, the disjunction distributes over the conjunction just as much. And the calculation is fairly similar. Let's take P conjunction with Q and then take the result and disjunction with R and see how that works. So, if R is true, then that means the disjunction will be true. Likewise, if the conjunction happens to be true, so true conjunction with true gives me true, that'll make the disjunction true. So if R is true, the disjunction is true. However, if the conjunction and R are both false, so true conjunction with false gives me false, and then disjunction with another false gives me false at the end. Flip that around. If I have false conjunction with true, that's going to give me false, but disjunction with the true gives me true. Unfortunately, if you flip the R to false, then that gets me double false, within disjunction will give me false. If you have double false, that guarantees the conjunction is going to be false, but if R is true, that saves the disjunction. But if R flips to false, then that guarantees that the disjunction will be false also, which gives me my pattern. True, 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 false, true, false, true, false will be the pattern here. Now, if I was able to distribute, the result should be this. I will take P disjunction with R, Q disjunction with R, and then conjunction the results. So let's see how that goes. If R is true, then both columns of this junction will be true, giving that the conjunction will be true. If P and Q are both true, that makes both of these disjunctions true, which makes the conjunction true. If R is true, both disjunctions are true, making the conjunction true. However, if Q is false and R is false, that'll make Q disjunction R false, making the conjunction false. If R is true, then both of these columns will be true, making the conjunction true. Over here, however, if I switch that and make P false and R false, that's going to make the disjunction between P and R false, making the conjunction false. If both P and Q happen to be false, R will make both of these true in the disjunction, making the conjunction true. But if all three are false, unfortunately, then that's going to make both columns false, which makes the conjunction false, giving me the pattern true, 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 false, true, false, true, false, which is the same as this column here. Thus, if I look at the equivalence, true equivalent to true is a true statement. Same thing with false equivalent to false is also a true statement, giving me the tautology. Thus, one can say that the disjunction distributes over the conjunction. However, notably, since the disjunction and conjunction distribute over each other, how different are they? You've probably noticed as we've been going through these charts, you've probably noticed that a lot of the charts look similar, just either reversed or with the true and false is reversed. So, what's going on here? How different are conjunction and disjunction? The next property clarifies the entire matter with the negation. Recall, the conjunction is only true if both statements are true, and the disjunction is only false if both statements are false. Hence, the two already appear to be negations, which actually gives me the following relationship. I'm going to take P conjunction with Q and then throw a negation on top of that. So, if I do so, true, true becomes true, which flips over to false. True, false gives me false, which flips to true. False, true gives me false, which flips to true. And false, false gives me false, which flips to true. Now, I look at this pattern, and I notice that's basically the disjunction's truth table, but flipped upside down, which I can accomplish by doing this. I negate P, I negate Q, and then take their disjunction. So true, true becomes false, false, which gives me false. True, false gives me false, true, which gives me true. False, true gives me true, false, which gives me true. And false, false becomes true, true, which gives me true. And I now look at this column and this column, and I see that they are indeed identical. So when I look at the equivalence, false is equivalent to false is a true statement. True is equivalent to true is also a true statement, giving me the tautology. Thus, indeed, the negation distributes in a way. It changes conjunction into disjunction along the way, which is why we use the V and the wedge symbols, because the negation flips one into the other one. Dually, the negation changes disjunction into conjunction the same way, which we do in the following way. Take P disjunction Q and put a negation on top of that. If I have true and true, that will give me true, which flips over to false. True, false gives true, which flips to false. False, true gives me true, which flips to false. And false, false gives me false, which flips to true, which, as you can see, looks very much like the conjunctions truth table, just upside down. Doing the same procedure as before, take negation P, negation Q, and then conjunction them and see where that goes. True, true becomes false, false, which yields false. True, false becomes false, true, which yields false. False, true becomes true, false, which yields false. And false, false yields true, true, which yields true. Notice again that the two columns are the same, so when I look at the equivalence, false is equivalent to false is a true statement, and true is equivalent to true is also a true statement, giving me the tautology. Now, both of these equivalences are actually called De Morgan's laws after mathematician and logician Augustus De Morgan. And moreover, De Morgan's laws show that disjunction and conjunction are on the same level, which illustrates why they were acting so similar. They're basically variations on the same idea. Though implications are not the main focus of this presentation, there are two important tautologies that should be discussed now. First, the implication can be reformulated in terms of a negation and the disjunction. Specifically, take P and Q. I'm going to think of P as being the hypothesis and Q as being the conclusion. What I'm going to do is negate P and then take the disjunction with Q and see what happens. Specifically, take true and true. If I negate true, I get false, and then false disjunction with true will give me true. Take true false, the negation of true will give me false, and then false disjunction with false gives me false. Take false true, the negation of false gives true, and true disjunction with true gives me true. Take false false, if I negate false, I get true, and then true disjunction with false gives me true. And I look at this truth table, and it looks starkly familiar. If you look at the implications truth table, true, false, true, true, they match up identically. Thus, the equivalence, true equates with true is true, false equates with false is also true, giving me a tautology. Hence, the implication can be derived, built from the previous two connectives, the negation and the disjunction. Second, the biconditional can also be constructed from the implication and the conjunction. Specifically, let's take P and Q as being members of this biconditional and consider P implies Q, Q implies P, and the conjunction of the two. So, true implies true is true, but true implies true is also true. Conjunction those gives true. True implies false is false, but false implies true is true. Thus, conjunction these gives false. False implies true is true, true implies false is false, conjunction those gives false. And lastly, false implies false is true, false implies false is true, conjunction these gives true. And I look at this truth table, and it looks starkly like the by implications truth table, which is true, false, false, true, as stated before. Thus, if I look at the equivalence, true is equivalent to true is true, false is equivalent to false is true, all the way down, giving the tautology. Thus, the biconditional is also derived from the previous connectives. Arguably, due to these equivalences and De Morgan's laws, one really only needs negation and disjunction in order to build all the other connectives we've talked about. Absolutely all of them. So if you're thinking about symbolic logic or hardware logic, OR gates and NOT gates, really, if you have an OR gate and a NOT gate, you can build all of symbolic logic in hardware. Now, in summary, having established several properties of the connectives, an order of priority can now be established. First and foremost, parentheses and other grouping symbols have highest priority as they serve to override any other priority that's given. Next, we have the negation. The negation is an unary operator acting on only one statement, so it has priority over all other binary operators that follow. Due to De Morgan's laws, conjunction and disjunction are basically on the same level, so we end up evaluating them in order from left to right the same way we would read English. Next, we have the implication and the biconditional, which are constructed out of the negation, conjunction, and disjunction by the previously established identities. Consequently, we evaluate them in order from left to right also. With this order of operations established, we can summarize the properties we've covered so far in the following nicer way by omitting some parentheses that are no longer necessary with the order of operations. Specifically, we have the absorption laws for conjunction and disjunction. We have the identities for conjunction and disjunction. We have the idempotent laws for conjunction and disjunction. We have some other miscellaneous laws like the law of the excluded middle, the law of non-contradiction, and the Tautologies law. We also have the commutative laws for conjunction and disjunction. We have the associative laws for conjunction and disjunction. We also have the distributive laws for conjunction and disjunction over each other. We also have the De Morgan's laws for conjunction and disjunction. We also have the restatements of the implication and biconditional in terms of the other connectives. And that's where we'll stop for today. Next time we'll pick up with properties of the implication. Below is a list of references for today's video. You have Magnus's For All X, Sears Grammar 101, Suppes and Hill's First Course in Mathematical Logic, as well as Suppes's Introduction to Logic. If you like today's video, go ahead and hit the like button below. If you have a comment or question, go ahead and leave that below as well, and we will respond to you as soon as we can. Thank you for your time, and we'll see you next time. See you then.